Hello, how are you?
Hello, Professor Chen.
You ready to talk today?
Yeah, maybe.
Maybe that's not a good answer.
I'm so nervous, but there should be 20. Oh my God. Okay, never
Yeah,
mind.
so we still have 40 minutes, 50 minutes. Well, Carlos, are you ready to present?
Yes, I'm ready.
Okay, so let me wait another half minute for more people to sign in. Sebastian, I'm glad you are here again. Welcome.
Hello. Thanks for inviting me.
Oh, yeah, okay, so great. So this is actually dual use. It's also part of the Meta Lab seminar series. I invited all the lab members to join us. So today we have three presenters. We have Carlos. After that, Jack. How you will be the last, all right? Okay. So without further ado, and let us welcome Carlos to give us a presentation. So your material are quite of lots of topics, so I guess you can use 5 more minutes if you.
Okay.
Okay, so don't rush too much. It's a very fresh topic, should be very interesting, and so Sebastian, you will love it. So, okay. So Carlos, the floor is yours.
Okay. Let me share my screen. Okay. Okay. Everybody see the presentation?
I can see it.
Yes, you can use a full screen.
Where? Where I?
If you click on swap displays, maybe that
Yeah,
will.
swap.
Ah, okay. I don't see where.
I see your next slide.
Yeah.
Okay, that's
Okay.
a good way to go. Go ahead, Carlos.
Okay. Well, hello everybody. My name is Carlos. Today I'm going to talk about developing of digital twin for a multivariable temperature platform. In this case, we use a Peltier device. So I explain that the outline, first of all, is we talk about digital twin, then what is the acronym of HELP, the platform, multivariable temperature control, the controller design and digital twin implementation, and finally the conclusion and future works. Then digital twin is revolutionizing the industry. So recently, numerous concepts about real digital twin are present in the literature. This is one of the concepts that I consider most complete, and talk about that the digital twin refers to the process and method of using digital technology to describe and model the characteristic, behavior, process, and performance of physical objects. And how we explain that? So here is a figure that in some way explain the principle of digital twin. So we have digital twin and the real system, that is the physical twin, and both systems change information. In this case, the real system send to the digital twin data and events and actions that we can use to performance, maintain, or analyze the health of the real system. In this case, for that purpose, we use virtual system model or virtual model instance and analysis result and history of the data. For that, we use model-based system environment to realize this analysis of the data. So in this case, the digital twin is available to realize adjustments and recommendations to the real system. In this case, for example, realize adjustment of the controller parameters or realize preventive maintaining a schedule. In this case, the majority of the digital twin in the field or in the the majority is focused in the preventive maintaining schedule. I don't see a more of work based in the adjustment of controller parameter or something like that. So here is the work, the paper that presents this concept. Another table that some author used to present the digital twin levels. This is this table where they represent the digital twin in 4 levels. The first level only analyze the physics-based simulation. The second one include the physical system. The third one include adaptive guide user interface. And the last one use machine learning, so you can analyze the data, predict some behavior of the system and something like that. Then after that, we focus in our project that is focused on the temperature control of a system, in this case Peltier, because the temperature is a physical property inherent in all systems. It's very important how we can handle this physical property. Also, recently, a special attention have been paid to thermoelectric elements like Peltier effect. Then, Peltier device is as you can see in this image, we use the opposite of the Seebeck effect, and using different voltage in the input, we can generate a flow of heat. And they have the capability to be small enough as the technologies require, and a lack of noise, vibration, and non-necessity of gas as other systems. Then FISP is acronym of Pixel Hearing Experimental Learning Platform. And here is a picture of the platform in his box. And the first block contains the Arduino board that communicates with the computer using serial protocol. The second one includes PWM servo and DC stepper motor driver to handle the voltage to each Peltier. The third one, a power resistor, because this power source handle 3.3 volts and 15 amperes. So the Peltier only admit 0.9 volts as input. So we can reduce the voltage. And the fourth block include the thermal camera to measure the temperature, and is connected to the Raspberry Pi using SPI protocol to communicate with the computer via TCP/IP. And the last one, this block contains the Peltier array that is formed by a 4x4 array of Peltier, as you can see in the next slide. And here is a heat sink to dissipate the heat in one of the sides of the Peltier element, and here a fan to exhaust this heat. So here is the system configuration, the computer connected to the Arduino. The Arduino send using digital ports the polarity of the voltage to the Peltier element to heat or cool depending of the control signal. The PWM generator receives the value of the frequency from the Arduino and send the PWM to the driver to generate the voltage that we need to send to the Peltier. This block, the camera and the Raspberry Pi connected with TCP/IP with the computer. Then the Peltier can handle value of temperature between 15 and to 100 Celsius degree. The input is 0.9 volts and 1.8 ampere. And the value to control the PWM are between minus 1096 to 4096, cooling and heating process. Here is an image in the center of the camera, in the left side, the heating process. And we use 16 green dots to represent the position of each Peltier. And this is the value of temperature that we are measured in our system to control the temperature. So using this surface of aluminum, we create the interaction between all the Peltier, and with this interaction, the dynamic can be represented by a MIMO system. In the left side, our first try, but it's not doesn't work because the airflow of the fan create perturbation in the temperature in the camera. So we have to eliminate this prototype, and we create another one where we put all the Peltier over the heatsink to, in the same way, dissipate the heat that the Peltier create in the other side when we are cooling this side. Then through the, as I say, aluminum surface can be modeled by integer or fractional order system, depending of the dynamic between the input and the output in the system. Here, the closed loop configuration using MATLAB Simulink, we send the control signal with serial port to the Arduino. The Arduino, send the frequency that we want generate with the PWM generator, and the driver send the voltage and current to the Peltier element, and we measure the temperature using the thermal camera and the Raspberry Pi. Then the identification process consists in apply a step signal in one Peltier and measure the temperature in all at the same time. Because of that, we got 256 data for the identification process. Here, an example using the first Peltier, the Peltier with the position in the first row and first column. We apply this step signal with the maximal amplitude, and this is the value of temperature in all the Peltier at this moment. So using this model, fractional first order plus time delay system, we find the parameters of this transfer function to characterize the dynamic between the input 1 and all the Peltier input 2, so in that way. So because of that, we obtain a matrix by 16 by 16, where the main diagonal are the transfer function of all the Peltier between the input in this Peltier and input and output in the same Peltier, and all the transfer function is the interaction between the Peltier. For example, in the first row is the input 1 related with all the Peltier. For the main diagonal, we obtain this transfer function. As you can see, the majority of the transfer function are represented by fractional order system, because as you can see, the value of alpha is less than 1. And we take it another data to validate the accuracy or performance of the model, and that was the result that we obtained for different feet. So I think that we can do better the next time. And as you can see, it's very good for a MIMO system. Then we use an optimal tuning algorithm based in the frequency domain, using based in the one of the book of Dr. Chen, that we can specify the dynamic of the system in frequency. Sorry, we can establish the response of the system that we want, and we using the transfer function of the system and the controller using frequency domain obtain the value of the controller. For this case, using phase margin between 60 and 65 and gain margin between 10 and 15, we obtain this value of PI controllers. So with this value, we create the closed loop of the system, and this is the response of the system for a step in the input. In this case, we apply the same input to all the Peltier. And in 170, we got a perturbation in the system created by the camera, because in certain time, automatically the camera apply some adjustment in the image to obtain a better quality of the image, and this process changed the value of the temperature. In the right side, you can see the control signal. We are working to obtain a more uniform control signal, because this variation can be again the healthy or durability of the Peltier device. Then we we use the same control signal that the real system and apply to the model that we obtain to the system, and this was the result of some Peltier. I don't put all the Peltier, so you can see better the performance of the system. It's good for now, but using some cost function, we can obtain better result of the MIMO system. The next step was create a more deeper model of the thermal process. In this case, we use a Simscape of Simulink, and with these toolbox, we can recreate each element of the system. In this case, we have the PWM generator, the H bridge, the resistor to reduce the voltage of the power source, and here we have the Peltier element that we can obtain the parameters of the Peltier using the data chip of the device. In this case, we realize a simulation with only 2 Peltier to be sure that consistency of the model. And the interaction between the Peltier was created using a thermal resistor. So the parameters of the Peltier, we use this equation that appear in MATLAB to simulate this device, and we found the Civic coefficient and the thermal conductance of the device using the parameters that appear in the data chip. So obtaining this value, we simulate the system and obtain this result using the same data that we use to simulate the MIMO system. And this was the results for the first and second Peltier in the first row. So with this result, we can continue adding the other Peltier to simulate the whole system, including the 16 Peltier. So as a conclusion, the platform was created for training and test different control strategy. The goal was achieved because both systems follow the dynamic of the system very accurately. The digital twin allows realizing the study of the physical system before implemented. That is more. This is one of the characteristics of the digital twin, that we can do simulation and analysis of the system before implemented in the real world, and take advantage of the result that we can obtain with the simulation. The design of the controller for the fractional first order plus time delay system is possible with the Funcom toolbox. Here is the link to the web page. And you can find there some documents as a guide for use these functions. And future works develop a supervisory interface for digital twin monitoring and smartness inclusion. Add some characteristic to the digital twin, as detect fault in each and all Peltier, detect fault in thermal camera, calculate the generation of the Peltier depending of the cycle, because this is this is one of the characteristics that this device presents as all the battery in our smartphone and computer, because with the time, the cycle of heating and cooling the device, the performance of the Peltier decrease. This is one data that the fabricant chose in the data sheet. Also install a temperature sensor in the heatsink to analyze how the temperature in the heatsink can affect the temperature in the surface that we are heating or cooling. Update the parameters of the digital twin in real time to achieve a better performance. Develop advanced control strategy for high order MIMO FISP system. And here a picture for the next step in the implementation of the Raspberry Pi as edge computing. And finally, upload the variable of the system, temperature, control signal, and reference for cloud-based analytics. In this case, I play with ThinkSpeak. Is a cloud of MATLAB that allows us send data to the cloud. Recently, I was sharing the temperature of the processor, of the Raspberry processor, and it's in real time. So as you can see here, this is the temperature. You can take this data, import to MATLAB, and realize anything you want with the data. For this is the reference that I use it. Thank you for your time.
Very good, Carlos. Did you mention about your EdgeX competition winning?
Yes.
Oh, yeah. For everybody's information, this is still internal news that they use this platform and participate EdgeX.com's competition. I think they won 10th place. It's very good. So congratulations. Any questions for Carlos? If you want to do MIMO control study or research, this is a perfect research platform. They can do 16 by 16, actually 16 by 16 input and output, right? So it's a very good system. Any questions from our audience here? Jairo, you don't want to ask something?
So maybe I want to mention something. I mean, Carlos has been working in this PHELP system since he arrived. One of the things that maybe takes long time is, the developing and, not only building the system, but also run all the tests to identify, to get the transfer function models, MIMO transfer function models, that was really time consuming. And I think also in the sense of digital twin, part of the next step is replicate the high order MIMO dynamic behavior that we have in a 16 by 16 system. Right now we are working with SISO and 2x2 system to work with the digital twin in the Peltier case. But I guess one of the challenges is represent properly this behavior, considering all the interaction that could be between all the Peltier array elements, and also, I mean, all the, the plate and many other physical components that we have, and represent this in the digital twin. I think this is the next big step. Probably that involves more about heat transfer concepts. In this case, considering also that we have thermal cameras. So probably, this is a kind of system where digital twin becomes valuable, in the sense that because it's too complex, and if we want to simulate any failure or any strange fault behavior, probably, for example, in the power unit management for these small Peltiers, if we run that failures on real system, we can break one of those small Peltiers, and that makes, it's not safe sometimes run some sort of test on the real prototype. In this case, using the digital twin, it's possible run this kind of test that could be dangerous on real life. And if we go to industry, it saves money in terms of if it's a big place like an oil refinery or something more complex.
Right. So this is called health and integrity of the control system. So if we have a control system, make it running, that's only the beginning. How to keep it running in a healthy way. So that's the reason we need digital twin. So we can introduce some artificial faults to see how system behaves. So that layer of artificial intelligence to make the system smart about all these faults, discovery of the fault, and even compensate. It's called fault tolerant control strategies. So all these things can be done in a research setting, but this is a class to introduce you and a possible platform to do MIMO control research. So in the interest of time, we should move on. So let's thank Carlos one more time. Thank you, Carlos. Thanks. So what's next? What I'm going to stop my recording.